Friends, now we will start discussion on transport phenomena and chemical reactions. That is, if you recall, so far we talked about the kinetics of various types of reactions, complex reactions in particular. So, now let us see how we bring in transport phenomena, particularly when you have heterogeneous reactions. Heterogeneous reactions imply that you have more than one phase, gas and solid or liquid and solid or gas, liquid and solid, and the reaction is occurring by interaction of reactants between these phases. Now, moment you have phases, you have boundaries which separate these phases, and the moment you have boundaries, there is a resistance for transfer across the boundaries, and hence the rates of the processes may actually go down because of this resistance for transfer, apart from the kinetic limitations that are present in the system. So, what we are going to do is we are going to start looking at gas solid catalytic reactions to begin with, and then we will turn our attention to non catalytic reactions and then gas liquid reaction. Now, to refresh our memory, what is the situation when a gas solid catalytic reaction takes place? For example, we discussed earlier that this is my catalyst pellet, then this catalyst pellet is present in the flow of gas, and I am going to now, so this is a gas which is flowing, this is my catalyst, and I am going to look at what happens to this gas as it tries to approach the catalyst. What are the transfer processes? You will recall we talked about external transfer, that is from the bulk to the surface. We also said there is a boundary layer, we will talk about that in a minute. Then from surface to inside the catalyst, then your chemical reaction, then again diffusion backward into the bulk. So, while we discussed about these chemical reactions so far, we would now start discussing about this transport in the bulk to the surface and from surface to the inside of the catalyst pellet. So, let us look at what happens when we have the catalyst which is exposed to the gaseous reactants and products. So, once again this is my catalyst, it is a porous catalyst. So, reactions are going to take place inside, but for time being we will focus only on what is happening outside. So, let us say that there is a gas which is flowing past this solid catalyst. So, it is a situation of flow past a solid surface. So, our reactants are, for example, for A and the product B is flowing past this catalyst surface. Now, when we talk about flow past a surface, we talk about hydrodynamic boundary layer, because what happens is that the velocity of the gas, for example, on this surface is 0 and it is flowing with certain velocity v outside the in the bulk. So, there is a transition of velocity from the bulk to the surface, and we say that the hydrodynamic boundary layer is a layer where this velocity is 99% of the bulk velocity. So, if you say this is a bulk velocity, this velocity at the surface is 99% of the bulk velocity, and from there it drops down to 0. when it comes to mass transfer, we will apply the same idea, that is, instead of hydrodynamic boundary layer, we will say that we have a mass transfer boundary layer. So, mass transfer boundary layer what is the characteristic of this mass transfer boundary layer? In similar manner to what we talked about in the velocity, that is, if concentration of A in the bulk is CAB, subscript B to denote that it is a bulk concentration, then the layer having a thickness delta, let us say. So, this thickness is delta, it is such that the outside edge of this layer, the velocity the concentration is 99% of CAB, and at the surface now the concentration can't be 0, or it may be 0 in certain cases, but it is not necessary, unlike velocity which is 0 at the surface, concentration may be something different. So, let us say that concentration is CAS. So, concentration at this surface of the catalyst is CAS, concentration at the outer edge of this boundary layer of thickness delta is CAB. 99% for all practical purposes we will take it as CAB. So, now we can visualize what is happening as the A from this boundary layer, there is a concentration difference, it has to be there. If the concentration difference is not there, then there can't be any diffusion, because the driving force for molecular diffusion is the concentration difference. So, there is a concentration difference, and that is what is resulting into the reaction. So, let us now enlarge this and say that this is my surface, this is my catalyst, and this is my boundary layer, one edge of the boundary layer having thickness delta. The concentration at this point is CAB, and at this point it is CAI, okay. And there is a drop in concentration from the outer edge to the boundary. Now, if I neglect, so now let us try looking at what is happening on the surface. What is happening on the surface? Right now we will say that the reaction is taking place only on the surface, because we have not brought in the internal diffusion yet. So, let us say that the reaction is taking place on this surface, and it is a first order reaction. So, on the surface the reaction at a rate RAI equal to, let us say, some rate constant Kr times CAI. We do not know what this CAI is at the moment, but let us say that concentration is some concentration CAI, and the reaction is taking place with that rate. We should keep in mind that the units of rate are, let us say, in kilomoles per meter square of the particle, because we are talking of surface area of the particle. So, that is why that subscript P over here, per hour. Now, the concentration of the species CAI is in kilomole per mf cube, that is, the concentration is kilomole per volume of the bulk phase, that is the fluid phase. Fluid is in all this phase. So, mf cube. So, Kr therefore, must have unit of mf cube by mp square per hour. Why I am pointing out this is we should always keep track of the proper dimensions, because any equation that you write, the dimensions of both left hand side and the right hand side must be equal. Now, the reaction rate constant over here has units of mf cube per mp square hour. It is same length m and m on numerator and denominator, but f subscript and p subscript over here. Okay. Now, let us see what happens to the mass in this boundary layer. That is the rate at which, this is the rate at which reaction is taking place, but there is also a rate at which material is or A is coming to the surface, and that is because of diffusion, external diffusion as we call it. So, mass transfer rate the flux in A, if we neglect the curvature effects and write the diffusion equation, we can show this as mass transfer coefficient Kg times the driving force Cab minus Cai. So, what is happening? So, let us say that this is my surface, the gas is flowing from the bulk or the boundary layer thickness to the surface, and it is reacting on the surface. Now, if I assume that this surface has no capacity to store mass, it has no capacity to store mass, then the rate at which A is coming to the surface and the rate at which it is reacting must be equal, or in other words, the reaction rate and mass transfer rate must be equal, or we can write Kr into Cai must be same as Kg into Cab minus Cai. Equality of mass transfer. What is the assumption we made? The assumption we made was that the surface is infinitesimally small, no volume, just the surface. So, it has no capacity to store mass. So, accumulation is not there. So, the reaction rate must be same as the rate at which the material is coming to the surface. If we take these two equations, and simplify a little bit, that is, if we take these two equations, this equation in particular, and simplify, we will get from solving for Cai, we will get Cai equal to Kg by Kg plus Kr Cab. That is, concentration at the interface is some fraction of the concentration at the bulk. So, just imagine that this line which you are seeing here is my interface, okay. That is the surface of the catalyst. So, concentration here is Cai, this is somewhere my boundary. So, that concentration is Cab. So, this concentration Cai is a fraction of this bulk concentration, and that fraction has both mass transfer coefficient as well as reaction rate constant into it. So, if we now take this Cai and plug it back into my rate, or in either this equation or this equation, it does not matter, we will get the rate of my reaction as Kg Kr by Kg plus Kr into CAB. My rate is also equal to Kr into CAI. That is my interface, but I am not interested because I do not know what the interface concentration is. So, I am interested in finding out what is the relationship between the rate of reaction and the bulk concentration, and this is that relationship. Now, we can compare these two and you will see that these are not same. Of course, this is written in terms of this constant is not same because this concentration is also not same. So, what can we write this reaction rate? So, first thing we notice here is that where my K naught is Kg Kr by Kg plus Kr. So, this is my K naught. So, my reaction was first order kinetics with the surface concentration, it remains first order even with the bulk concentration, but this is not true for all cases. This is true only for first order case. For second order case, it is not necessary that your rate constant is same. So, what it practically means is that when you do this reaction, this is the rate that you are going to measure and you are going to measure the bulk concentration. So, if you try to estimate the kinetic rate constant, you will get the value K naught and not Kr, because to get Kr you will have to measure the surface concentration, which we do not know. But what is the relationship between K naught, Kr and Kg? We can write this as 1 over Kg plus 1 over Kr. This will immediately strike a chord, those of you who remember your electrical engineering lectures, resistances in series, they add up. So, my coefficient or inverse of coefficient is like resistance. So, this is overall resistance, measure of overall resistance. This quantity is the resistance due to mass transfer 1 over kg, and this quantity is resistance or equivalent of that due to chemical reaction. Transfer coefficient and resistances are inverse of each other. So, now we can clearly see that if mass transfer resistance is high compared to chemical reaction, that means mass transfer value Kg is very much lower than Kr. That is the situation where mass transfer resistance will be high. So, what we see here therefore is that this is a situation of resistances in series. Overall resistance as an addition of resistance due to mass transfer and resistance due to chemical reaction. So, resistances are inverse of coefficients, transfer coefficient. So, higher the resistance, lower is the value of transfer coefficient. So, let us say that our mass transfer coefficient is very much smaller than the reaction rate constant. Okay. So, this for this particular situation, what will we get? 1 over kg will be very much large compared to 1 over kr, to the extent that we can neglect 1 over kr, and this would imply k naught is almost equal to kg. This when mass transfer resistance is large. Which implies that what does it imply? So, if you go back to our reaction rate, RAI is K naught into CAB, it is actually Kg into CAB. So, the rate constant that we will measure is not the reaction rate constant Kr, but the overall mass transfer coefficient if mass transfer process is very slow compared to the chemical reaction. What about the other situation? If Kg is very much greater than Kr, that means now reaction is very slow, this would imply K naught is almost same as Kr. So, when the mass transfer resistance is very small compared to the chemical reaction resistance, then the kinetic rate constant that we will measure or K naught is same as the actual kinetic rate constant. So, once again we note that K naught is an effective rate constant which is influenced by both mass transfer coefficient Kg and the reaction rate Kr. I will also emphasize that because of mass transfer resistance, our reaction or our rate overall observed rate constant is different. Now, let me reiterate this point, because this is an important idea which we will be using time and again. We said that my rate of reaction is K naught into CAB. When I actually do the experiments, I will be measuring these rates. So, these are my measurements rate, which we also called as observed rate. This is what I will actually measure. This is my concentration in the bulk, which again my experimentally measured quantity. So, when I do experiments, I measure this rate RAI for this particular concentration CAB. Now, and if I do some linear fit, I will get the rate constant which is actually the observed rate constant. Why is it observed rate constant? Because if you recall my true reaction rate is Kr into Cai. So, this is my true rate constant. But I will measure or I will observe K naught. Are these two same? They are, if mass transfer resistance is very small. So, if K naught is very much similar to Kr, that is when mass transfer resistance is negligible, then we are measuring the true kinetic rate constant. But if mass transfer resistance is very high, where K naught is almost equal to Kg, the mass transfer rate, what we will be observing is the mass transfer coefficient rate, coefficient rather than the kinetic rate constant. So, this also implies the following. So, we are looking at the relative value of Kg and Kr. For example, when it comes to temperature effect, you will recall that our Kr varies as 1 over T in a linear manner if you are plotting ln, let us say, okay, because Arrhenius rate relationship. Now, this is temperature low, this is temperature high. Now, what happens when you increase the temperature from low value to high value? The Kr value or the kinetic rate constant increases. That means, the probability that Kg will be less than Kr is much higher towards this end rather than this particular end, or in other words, if this is what happens, then what reaction rate we will measure. So, if we are now saying that we are looking at observed rate constant, then what will happen? At low temperatures, it is likely that Kg is higher than Kr. So, I will measure the same reaction rate. But as I am increasing the temperature, the mass transfer will start becoming limiting and my reaction rate measured will deviate from the true constant. So, this is my Kr, this is my K naught. Mass transfer coefficients are typically very weak functions of temperature, unlike reaction rate constant, which is an exponential function. Now, how do we get this mass transfer coefficient? Recall that we said that this is a surface, this is my boundary, thickness delta. So, we can find the mass transfer coefficient, that is, if we actually write the diffusion equation, we can show that it is nothing but diffusion coefficient of A in the mixture AB divided by the thickness of the boundary layer. Mass transfer coefficient is something which is not a property like density or mass which you can actually measure, it is there. This is a concept. So, we have to estimate it. How do we estimate this? We use typically various kinds of correlations. For example, Reynolds number, particle diameter, superficial gas velocity, viscosity, Sherwood number, Kg dP by dAB, dP is the diameter of the particle, Kg is the mass transfer coefficient, dAB is the diffusivity, and the Schmidt number, mu by rho f into dAB, viscosity divided by the density of the fluid dAB. So, for example, Froschling correlation is Sherwood number is 2 plus 0.6, Reynolds number raised to 1/2, Sherwood number raised to 1/3. If the gas flow is very low, that means almost flow past almost a stationary flow, Reynolds number will go to 0. So, Sherwood number equal to 2, that is correlation you might have already seen. Or we use the correlations such as JD factor, which is Kg rho f by G into mu by rho f into dAB raised to 1/2, and this JD factor is a function of Reynolds number. For example, what we see here is Reynolds number on the x axis and JD factor on the right hand side over here, and this is a fairly straight line correlation between JD and Reynolds number, and these are efforts by different researchers showing that the relationship is fairly straight line. When it comes to heat transfer, we could have the similar argument, except JH now, JH for heat transfer is defined as HF by Cp into G into Cp mu by K. What is that? That is Prandtl number raised to 2/3, which is also a function of Reynolds number. And you can see once again a different correlationship with different researchers have found between these two factors. So, these correlationships, what they tell us is that mass transfer coefficient depends on various properties of the reacting mixture. For example, if we take all this Froschling correlation or even this JD factor correlation, we find the mass transfer coefficient is proportional to diffusivity raised to power 2/3 and kinematic viscosity nu raised to 1/6 multiplied by u, that is the velocity raised to power half, by dP raised to power half. Now, mass transfer coefficient Kg, kinematic viscosity mu by rho. So, these is a function of temperature and pressure, whereas these are the property of flow conditions, the velocity as well as the particle, what particle size we have. So, for example, what happens for gases and liquids as we increase the temperature? As temperature increases, DAB increases. So, the mass transfer coefficient will increase in the value. However, what happens to kinematic viscosity? For gases, as we increase the temperature, kinematic viscosity also increases, whereas for liquids, as we increase the temperature, kinematic viscosity decreases. So, depending upon whether we are looking at gas solid system or liquid solid system, temperature will have different effect on mass transfer coefficient, but whatever it is, it's weak compared to the effect of temperature on the reaction rate kinetics. For example, this u by dP, u is the velocity and dP is the particle size. So, this clearly says that higher the velocity, higher is the value of mass transfer coefficient, lower is the size of the particle, higher is the mass transfer coefficient. In fact, we can put these results together and say that if you try to look at the observed rate against u by dP, okay, raised to half, we typically see a behavior like this. What does this behavior mean? Now, if our reaction is controlled by kinetics, that means mass transfer is very fast. Okay. So, if mass transfer is very fast, whether you increase u by dP even more, the mass transfer rate is going to be even more, but that is not controlling. What is controlling is the reaction rate. So, u by dP has no influence on the observed rate if reaction is kinetically controlled and not by mass transfer control. So, this is the region of our kinetic control. Whereas, if u by dP is very small, then your Kg values are small, that means mass transfer resistances are large. So, we are in a diffusion controlled regime. So, this is my diffusion control regime. So, we can actually find out by doing experiments, same concentration, same temperature, pressures, everything is same, except we change the velocity or the diameter of the particle, and then if we get results something like this, we can identify the regimes under which reactions are kinetically controlled, that is the rate is independent of variation in u or dP, then this is that region. If it is diffusion region, then rate will increase as we increase u by dP, and then of course, there is a transition region. So, knowing Kg, and when it comes to mass transfer Kg, heat transfer coefficient HF, we can keep the same arguments for temperature as what we did for energy. The only difference is, instead of rate of reaction, we will now equate rate of heat generation to rate of energy transport, energy generation because of chemical reaction. So, now let us start looking at what happens when we have these gas solid reactions, and let us take a closer look at the catalyst. What we discussed today so far is what happens when we are looking at the external transport, but that is not the only thing that is happening. What we learnt from this discussion is that depending upon whether mass transfer rate is low compared to the reaction rate, the overall observed rate could be determined by the mass transfer rate. If the kinetic rate is smaller compared to the mass transfer rate, then the overall rate will be determined by the kinetic rate. We call that as kinetically controlled regime. So, now let us look at what happens when we have this gas solid reactions, but before we go there, this is just a slide showing the catalyst. This was given to me by Professor David Agar, so I must thank him for this. Just showing that catalyst does not come always in the same shape and size. In fact, what we see here is that this can be a hollow cylinder as seen over here, or small cylinders, granular spherical tablets, or cylinders with high L to D ratio, or very fine powders. So, catalysts are of different type, and not only of different size, they are of different color also, which you can clearly see over here. They come in all size, shape and color, green, blue, yellow, red, you name it and we have it. This is again a cartoon illustration of what actually is happening. This is, let us say, my cylindrical catalyst. If you enlarge it, you see small pores on the micron level size, you will see the catalyst material deposited, and these are in fact the real ACM photographs and micrograph of course of the same material. This is a cartoon representation. Our reactor is of the type of meters. So, this material is going to be sitting in a column which is of the length meter or so. So, when we talk about diffusion, we have to talk about diffusion at various different length scales, from meso to micro, from meters and centimeters to millimeters to microns, and maybe these days even to nano level. So, this figure over here illustrates what happens as a function of position to both the concentration and the temperature. Let us focus on concentration. So, what we said just now, this is my catalyst pellet which is porous. So, material has to diffuse inside. This is my bulk and this is my boundary layer in which the entire resistance to mass transfer is located. So, what happens here? What happens is the concentration far away from the surface of the catalyst is the bulk concentration. It reduces to surface concentration CAI because of resistance to the mass transfer outside the catalyst, and then the concentration decreases gradually as we move from the surface to the center of the catalyst, and being symmetrical, the same thing can be seen from the other side as well. So, what we have is actually the concentration decrease. Now, why is this concentration is decreasing inside the catalyst pellet? Outside the catalyst pellet, the concentration decrease is only due to mass transfer, but inside the catalyst pellet, the concentration decrease is not only because of mass transfer, but simultaneous chemical reaction, because the reaction is taking place inside the catalytic pellet. So, we have to worry about reaction and diffusion taking place simultaneously. Same thing can be said about temperature. Far away from the surface, far away from the surface of this catalyst, the temperature is some bulk temperature Tb. Closer at the surface, temperature is Ti. We are assuming this reaction is exothermic. So, temperature from the bulk is lower than the temperature at the surface. Reaction is taking place inside. So, heat generation source is there inside. So, temperature is even further increased, and then the symmetry from the other side. So, this cartoon which we will be using time and again to set up our mass balances or similar cartoons. Once again, before we move forward, the center of the catalyst pellet, this location over here, the surface of the catalyst pellet and the outer layer of the boundary. Typically, we will say that catalyst, there is no preferred direction, the material can diffuse in and out from any direction. So, there is a symmetry, and whenever there is a symmetry, you will see the slope of the line is 0 at the center point. So, if I call position as radius r and C as concentration, we can easily write dC dr equal to 0 at the center point. Okay. Concentration here is CAI, concentration here is CAB. Same thing can be written for temperature. dT dr is 0 at r equal to 0, and C is equal to CAI at r equal to capital R, if you are talking about a spherical catalyst. Before we go to the actual reaction and diffusion simultaneously, let's look at the diffusion aspect. Now, in case of binary diffusion, the diffusion between A and B is given by correlations such as what we see over here. Correlations such as D12 for example, which involves temperature, which involves, these are Fuller Giddings correlations. I mean, there are similar correlations for other researches also, but by and large they are more or less same. So, my diffusion coefficient D12 depends on temperature, it depends on temperature, molecular weight of two species and distance between the two species or their molecular diameter and so on. For example, for gases, the diffusion coefficients are of order of 10 raised to minus 1 centimeter square per second. For liquids, the diffusion coefficients are much lower, about 10 raised to minus 5 centimeter square per second. And we all know that diffusion is a result of mass transfer, both because of that is the total mass transfer is both because of diffusion, which we write using Fick's law, diffusion coefficient times the concentration gradient, and due to bulk motion of the species. So, Y1 into N1 plus N2. This is my flux of. So, what it says is the diffusion is a result of interaction or the movement of these two molecules as well as the movement of the entire flux. Now, when it comes to multi-component, in a reacting species you will have multi-component system, and for multi-component system these equations, Stephan-Maxwell equations are available, but those are not very convenient to work with. So, what we have is effective diffusion coefficient dJm, which is Nj. So, equivalence to binary system, we have multi-component diffusion, again dJm, where dJm is actually not true binary coefficient, because here when you have more than one component ABC, let us say, or 1 2 3, we have diffusion coefficient binary between 1 and 2, 1 and 3, 2 and 3 and so on. So, the all those things put together will determine the what is called as effective diffusion coefficient. So, if you are looking at the jth species, then the flux of the species Nj is given by the effective diffusion coefficient of J in the mixture, and that is why we call it as dJm. Is of course the fixed diffusion, molecular diffusion equation, concentration gradient multiplied by diffusion coefficient plus the flux due to the bulk motion of the fluid. What is this effective diffusion coefficient dJm in the mixture? One can show it is related to the composition of the mixture. So, Y mole fraction and this formulas Nk by Nj and so on. This equation may look little complicated at the moment, but let us consider few simplification. For example, if I say that for all pairs djk, that is let us say d12, d13, d23, if you have a ternary system, if all of them are equal, then as you would expect djm, let us say this is some value d, will reduce to. So, if you put that all d values are more or less equal. So, this comes out and djm becomes simply oh, this should be 1 over djm. Okay. So, that is one simplification. The other simplification that is possible is, let us say that we have a mixture where one of the component is dominant. So, let us say that y1 is far greater than y2, y3, y4. Okay. So, all other components are present in the dilute quantity. Then if we therefore then assume that Nj flux of all other quantities is more or less similar, then if we simplify this equation, we get djm equivalent to d1 or rather dj1, that is the mixture behaves as if it is a single component mixture. Okay. Another simplification possible, let us say that all these species are reacting with a certain stoichiometry. So, let us say that our reaction is nu j A j equal to 0. Then we know that from our earlier discussion, the fluxes of two species N j and N I must be related by their stoichiometric coefficient. Okay. So, we can further simplify this diffusion coefficient. We will stop here. So, what we are going to what we actually saw in this class is about diffusion, both external, and we started little bit of diffusion coefficient discussion for inside the catalyst pellet. But now comes the real test. What actually happens when these gases try to diffuse inside the catalyst pore whose dimensions are of micron sizes? What happens to the diffusion phenomena? This is where we will start in our next session. Thank you.